Hello viewers, welcome to Exploring Technologies. In this video, I will explain about the fuzzy logic controllers. I will explain its basic theory and its implementation in Matlab. So let me start this video with the contents first. First, I will explain what is the need of the controllers in control systems. Then I will explain the classical controller versus fuzzy logic controllers. Then we will see inside the FLC, its basic architecture. Then we will see the design process of an FLC for a throttle control system, highlighting all the three major steps of fuzzification, rule-based implementation, and then de-fuzzification. In the last, I will explain the implementation of this design FLC in Matlab and its simulation. So let me start this lecture. So let me explain what is the need of the controllers. Actually, if design system does not satisfy based on the following parameters like rise time, overshoot, steady state error, or phase margin, etc., then controllers are actually used to achieve the desired response. So you can say that controllers are actually the system response modifiers. A controller is mainly introduced with the main plant transfer function in feed forward loop as shown below. So this is a plant in a feedback system, and this is the controller. So here controller is actually modifying overall system response by relocating the poles at the desired locations by modifying the overall system transfer function. So now let's see the classical controller. Actually, the placement of the classical controller is shown in this figure. In this system, this controller actually works on the crisp input values and provides the crisp output values. So here controller has actually a precise mathematical model. So this mathematical model may contain the input-output relations in form of either differential equations or difference equations in time domain. And if you're talking about the frequency domain, this mathematical relationship is in form of the transfer function as shown here, like GCS. And examples are like PI, PID controllers. These are classical controllers. So now let's see what is a fuzzy logic controller actually. Just recall the previous figure. The placement of FLC is same as of the classical controller. I mean, connection wise, they both are same. But in many situations, it is not possible to obtain the precise mathematical model of a controller due to the system's complexity. So in such case of vague, ill-defined, and the complex system model, the one impressive solution is the fuzzy logic based controllers. So while designing FLC, actually designer faces the problem of selecting input-output variables, membership functions, and then fuzzy rules. So that is actually the main difficulty. So the success of the design actually depends on the designer's experience. So in another approach, FLC can also be combined with these conventional, the classical controllers. So that gives actually the mixed control strategy. So in this video, I'm just talking about the FLC only. So now let's see what is inside the fuzzy logic controller, its basic architecture. So actually FLC works on the fuzzy values, not on the crisp values. So both the inputs and outputs are fuzzy in nature. So, but we know that real world quantities are not fuzzy, they are crisp, such as some voltage or current in magnitude. Therefore, conversion from crisp to fuzzy and fuzzy to crisp are required for the FLC. So the block diagram is shown here. So this is your crisp input. So first you have the fuzzifier, which changes these crisp values to the fuzzy values. Okay. And similarly, at the output stage, we have the de-fuzzifier, which converts the fuzzy values into the crisp output value. So that can be given to the plant. Here we have the rule base where all the rules are defined, and this is the inference engine. So on the basis of the inputs, it activates a certain rules, okay, and gives a fuzzy output. So all these fuzzy outputs are aggregated, and then they are de-fuzzified to get a single crisp output. So FLC can be MIMO, multiple input, multiple output systems. It can be designed even the plant model is not known. Even if you don't have any idea about the mathematical model of the plant, still you can design the FLC. So now let's see the its basic steps. What happens inside the fuzzification. So fuzzification is the process of transforming physical crisp values to the fuzzy values. So this is actually a mapping process where a crisp value is mapped into the fuzzy subset with the help of some membership functions. So these membership functions actually assign the degree of the membership in the range 0 to 1 to those crisp values. So there are several types of membership functions such as triangular, Gaussian, trapezoidal, singleton, sigmoid, etc. Depending on the requirement, we choose the appropriate membership functions. So here in this example, you can see that how the crisp values are fuzzified. So we have the two fuzzy subsets, normal and hot, for the temperature T, and this is my input temperature, let's say some T degrees Celsius, that is a crisp value. So you can see that this crisp value is cutting this normal fuzzy subset at this point, and it is cutting the hot at this point. So I will say that this crisp value is 75% belonging to the normal set and 25% to the hot fuzzy subset. So this is how your crisp values can be fuzzified in the fuzzy logic. So now come to the fuzzy rules. They are also known as the if-then rules. These fuzzy rules are actually defined by the designer on the basis of the requirement. It actually requires the experience. So these rules relate input and output side membership functions. So actually their structure is if-then structure. For example, if your system has single input, then the rules structure will be like this. So for example, if input is A, then output is B. Okay. If you have the multiple inputs, let's say 2 inputs, then the structure will be like this. If service is excellent or food is delicious, then tip is more. So this is the case for multiple inputs. Here we have used the 2 inputs, service and food, and the output is tip. Similarly, this is another statement. If temperature is high and humidity is high, then fan speed is more. So here the temperature and humidity are 2 inputs and the fan speed is the output. Okay. So what is the difference between these two rules? Here the difference is of these operations, or and AND operations, right? So these are few examples of fuzzy rules. Here if part is known as the antecedent and then part is known as the consequent. So here antecedent relates input side membership functions while consequent relates output side membership function. So now let's see what is the de-fuzzification. For a particular crisp input, several fuzzy rules are activated. So according to these activated rules, the output of the inference engines are some aggregated fuzzy sets, okay, not the crisp values. So from these aggregated fuzzy sets, we need the single crisp value so that it can be used as a control signal for the plant. So de-fuzzification is actually the process of converting aggregated fuzzy sets into the single crisp value. So we have the several methods used for de-fuzzification, such as center of the gravity, weighted average, mean of max, etc., where the COG is very common for FLCs. So this is an example of the de-fuzzification. So here you can see that these two sets are aggregated. So you are getting this total final yellow area as a fuzzy output of the inference engine. So to convert this into the single crisp value, so we have used the center of the gravity method. So for this overall yellow area, we have found this crisp value, some T degrees Celsius as the output. So that is the use of center of gravity. We can use other methods also. And now let's see the example that how we can design a fuzzy logic controller for a certain application. So here our objective is to design a fuzzy logic controller for the throttle control for a steam turbine. So here inputs are actually the temperature T and pressure P of the steam, and the output is the rotation of the valve. Okay, so that is the rotation angle theta. So this is your controller for FLC. Inputs temperature and pressure, and the output valve rotation angle theta. So here we are taking the range of the temperature from 300 degrees Celsius to 600 degrees Celsius, and we are taking range of pressure of steam from 500 to 1000 psig, and range of the valve rotation angle from -90 to +90. So we are assuming that this is a valve at 0 degree, it is at the normal position, so you can rotate it to the left side till 90 degree, and you can rotate this to the right side to 90 degree. So total rotation is from -90 to +90 depending on the control action. So now the first step is fuzzification. So we have to define the fuzzy subsets. So we are first defining the linguistic descriptor for the each fuzzy subset. We have the two inputs, temperature and the pressure. So we will define the linguistic descriptor for both temperature as well as pressure. So for temperature, we have taken the three descriptor: normal, hot, and super hot. And for pressure, we are taking low, normal, and high. And for valve rotation angle, we have taken total 5 linguistic descriptor: 0, that is Z, and then the left side rotation, small rotation, that is negative small N1, or negative large, that is N2. And for right side rotation, the positive small P1 and the positive large P2. So now let's talk about the membership function assignment, that how we can assign the membership functions for both the inputs. So first we'll talk about the temperature. So this is how we have assigned the membership functions. Here we are using the triangular membership functions. You can use other shapes also. So for three linguistic parameters, normal, hot, and super hot, we are assigning these membership functions. So this is our input range from 300 to 600 degree Celsius, right? And the output is always be from 0 to 1. That is the degree of the membership. And similarly for pressure, we have used again the three membership functions for low, normal, and high for the range 500 to 1000 psig. Okay, and now let's talk about the output valve rotation angle theta. So we have used the 5 triangular membership functions: Z, 0, positive small, positive large, negative small, and negative large. Range we have already decided, -90 to +90 through -45, 0, and +45. So 0 is the mean position of the valve. So now let's talk about the fuzzy rules, how to define the fuzzy rules. As I said, this is the difficult part and it depends on the experience of the designer. So we have the 3 membership functions for each input. We have 2 inputs, so total 9 rules will be designed. So this is how we have arranged all these rules in a tabular form. So here you have the temperature, so normal, hot, and super hot, and here you have the pressure, low, normal, and high. And here you have given the output action of the valve. I mean, if temperature is normal, pressure is low, then your output is P2. I mean the positive large, so you will open the valve. If your temperature is normal, pressure is also normal, then output action is Z, do nothing. If temperature is normal, pressure is high, then your action is negative large. I mean, you just close the valve like that. Similarly, for all combinations, you have these output actions. So design is complete at this moment. So now we will examine how this FLC will create the output for a particular crisp input. So for that, we can see how the rules are fired and how the de-fuzzification takes place. So now I'm considering one crisp input case where temperature is, let's say, 400 degrees Celsius and the current steam pressure is 700 psig. So in this current situation, what will be the corresponding output of this FLC. How much valve it will open in left side or right side, how much angle the valve will rotate. Let's see. So what we have to do, we have to draw the membership functions of temperature and the pressure. Okay. So now you draw one vertical line for 400 degrees Celsius, this one, and for vertical line for pressure 700 psig. So here you can see that this line is cutting at the 2 points. There are 2 intersection points. It is cutting the hot as well as normal temperature. It is cutting the normal pressure and the low pressure. Okay. So we get the 4 intersection points, hot and normal in the temperature and normal and low in the pressure. Okay. This is for T and these 2 are for pressure. So because of these 4 intersection points, total 4 rules will be fired. So let's see how. So what we will see, we will actually make the combinations of these 4 points. I mean, for example, that this is a hot intersection point. So I will say if if temperature is hot and then pressure is normal, what is the output action? If temperature is hot, pressure is low, what is the output action? Similarly, if temperature is normal, pressure is normal, then what is the output action? If temperature is normal, pressure is low, then what is the output action? So that we will search in that rule table. So let's see how. So I have written all these 4 rules, that when temperature is normal and pressure is normal, when temperature is normal, pressure is low, temperature is hot, pressure is normal, and temperature is hot and then pressure is low. So what will happen? What will be the output action? So just recall that table. So we'll take the rule 1. When temperature is normal and pressure is also normal, then obviously the rule fired is this. That means output is Z. Do nothing with the valve. For R2, when temperature is normal and pressure is low, obviously P2 is fired. Rule 3, when temperature is hot, this one, and pressure is normal, then this is the rule. Rule 4, when temperature is hot and pressure is low, then this is the rule P2. So we have these 4 rules that will be fired for this combination of the temperature and pressure input. So let's see how we'll get the output. So now draw all the membership functions side by side like this. You can draw this on a graph paper also with a certain scales. So we'll first show the rule 1. Rule 1, okay. So this is the horizontal line which is showing that the temperature is normal. When temperature is normal and pressure is normal, what is the output? Output was a Z. Okay. So since here we are using the AND operation, so we are using actually the min operation. So we will highlight the minimum one. So since output action is Z, so we will take the minimum value and we will highlight this area under the Z membership function. So this is the rule 1 activation is complete. Now come to the rule 2. Okay. In rule 2, when temperature is normal and then pressure is low, then output is P2. And since because it is a AND operation, so we will highlight the minimum area, okay, under the P2. So this is the P2 rule is activated. So now 2 more are remaining, rule 3 and 4. So let's come to the rule 3. When temperature is hot, okay, that is a hot intersection point, and the pressure is normal, your output is Z from that table which we have already discussed, and because of the AND operation we'll highlight the minimum area under the Z, right? So rule 3 is complete. Similarly, rule 4, where temperature is hot and the pressure is low, the output is P2 from that table, and because of the AND operation we will highlight the minimum area, right? So we have seen the activation of all the 4 rules here. This exercise, if you want to do the manually, you can do this on the graph paper. Okay, so you can get the actual values of these points, all the numerical values of these heights. So now we'll do the aggregation. So first, let's see the area under the Z. In 2 rules, R1 and R3, we got the Z output. Okay, in 1 we are getting this much height, in R3 we are getting this much height. So which one we have to take? Here for aggregation we actually go for generally OR operation. So OR operation means the max operation, so we will take as a max area, maximum height, I mean this one. So let's say this height is mu1, so that is my aggregation of the area under the Z. Similarly, in the remaining 2 rules, I mean R2 and R4, we are getting the area under the P2. Okay, so again we will apply the OR operation and we will aggregate and we get the single outcome as this, which one is the larger. But if you draw this on the graph paper, you will see that in this particular case both are having the same magnitude, same height. Okay, so we are getting this, let's say this height is mu2. So now you just put all the aggregated areas together for the de-fuzzification. So under the Z we are getting this mu1 height, under the P2 we are getting this mu2 height. So just consider this as a single combined area, and now you have to do the de-fuzzification to get a single crisp output. Okay, so these are actually the fuzzy values and we have to get the output using the de-fuzzification. So here I'm applying the center of the gravity. So with the help of the center of gravity I find this as COG. So on x-axis, I mean on angle axis, let's see how much angle is this. This is a plus 12.0298. So it means for 700 psig pressure and 400 degrees Celsius of the steam temperature, this FLC will create, or it will open the valve 12 degree in clockwise direction. I mean this is a Z point, 0 point, and it will be slightly open the valve to let the steam pass more steam. So that is 12.0298 degree. Okay, so this is how the FLC gives output. So for any input combination you can try within the range of temperature and pressure. You can try any combination and you will get the output. So this is the complete process. I hope you have understood this process. If you want to do this manually, you can do this on the graph paper. You follow all the steps on the graph paper with a certain scales. You will get this 12.0298 degree. Okay, manually also. So now the time to implement this in Matlab. So here I will show you that how you can implement this FLC in Matlab. So let me jump to the Matlab, and this is my Matlab. So to implement this, you have to take the help of the one ready-made application. So go to the application tab and search for fuzzy logic designer. So under the control system design and analysis, you will get this fuzzy logic designer. Click it, you will get this GUI. So here you can see a default of FLC having single input, single output, and so these are the input membership functions, and these are the output membership functions, and in between this is a rule base block. So since our system has the 2 inputs, so we have to add one more input. So go to the add variable input. So now you have the 2 inputs. Okay, you can see 2 inputs. So now just go to the input 1. You can change its name. Default is input 1, so you go to change the name. Let's say let me write the temperature, and for second let me write the pressure. Okay, temperature and pressure. And similarly for output, you can change the name, let's say theta is my output. Okay, so now let me define the membership functions. So just double click this temperature block. So here by default you have membership functions. Better to remove all these membership functions. So go to the edit, remove all MFs. Okay, so you have a blank window. Now go to the edit again, add MF. Okay, so from here MF type, you can choose any membership function type like Gaussian, bell type, trapezoidal, etc. So here I am using the triangular, so that is by default triangular membership function, and the number of membership functions. So as we have seen that we have chosen the 3 membership functions for temperature and pressure input. So just press OK. You get these 3 membership functions. So their default name is MF1, MF2 and MF3. You can change their name from here. So this is actually we are working for the temperature. So for temperature we have taken the name. Let's see which name. For temperature we have 3 linguistic variables: normal, hot and super hot. So the first one is normal, and then second one is hot, and third one is the super hot. Okay, so this is how you can assign these linguistic parameters. And now see the range. Range default on x-axis is from 0 to 1, but our range was from 300 to 600 degrees Celsius. So here we will give this range 300 to 600. You just press enter, so your range is changed from 300 to 600, right? Similarly, I will go to the pressure and then add it, remove all the MFs, add it, add MFs. Okay, so 3 membership functions are added. Now I will change their name. Instead of MF1, my linguistic assignment is low, normal and high. So this is the low, and second one is the normal, and third one is high. Third one is the high. Okay, and change the range. Range is from 500 to 1000 psig. So 500 to 1000. Okay, press the enter, so your range is changed. And now come to the output theta. Again go to the edit, remove all MFs, add it, add MFs, and instead of 3 choose 5, because we have defined 5 membership functions. So these are 5 default membership functions. Change their name. The first one is the N2 negative large, second one was the N1 negative small, the middle one is the 0, that is a Z, this one is the P1 positive small, and this one is the P2, that is large positive. And then change the range, that is from minus 90 to plus 90. Okay, so range is changed, you can see, from minus 90 to plus 90. So this is how all the membership functions are defined. Now close it and then go to this middle block, that is your rule actually. So go to the rule, fuzzy rules, double click it, and here you will get this GUI where you can add all the 9 rules. Okay, so to add the 9 rules you need that table. So I will recall that table. Where is that? This one. Okay, so this is my table. Okay, so now I will define all the 9 rules. So I will take the first combination when temperature is normal. You see both the list here. This is first for temperature, second is for pressure, and third one is for theta. So when temperature is normal, you just select normal, and pressure is low, right? So what is your output? Your output is P2. You just select P2. So temperature is normal, pressure is low, and then output theta is P2. So you just add. So the first rule is added. Now go to the second rule, where temperature is normal, pressure is normal, then output is Z. Add rule. When temperature is normal, pressure is high, and then output is N2. Add rule. So the first row is added. Now the second row, come to the second row. When temperature is hot, pressure is low, your output is P2. Add rule. Temperature is hot, pressure is normal, your output is Z. Your temperature is hot, pressure is high, and then output is N1. Add rule. So second row is added. Now come to the third row. Your temperature is super hot and pressure is low. Your output action is P1. Add rule. And then temperature is super hot, pressure is normal, your output is N2. Your temperature is super hot, pressure is high, then output is N1. Add rules. Okay, so all the 9 rules are added. I mean, this table is completely added here. All 1, 2, 3, 4, 5, 6, 7, 8, 9 rules. Okay, so you just close it. Let's see other things also, like connection. Connection is the end. Okay, so in the theoretical part also we have used the end operation. I mean, minimum will be chosen during the rule firing. So you can have the options of OR also, but we are taking the end operation here. So don't change anything else. Just close it. So this model is complete. This fuzzy model is complete. So this fuzzy model is complete. Okay, and see the end method is the min method here, or method is the max method, and the aggregation of those fuzzy set is the max, and the de-fuzzification is the centroid. You can choose other also, centroid, bisector, max of mean of max, like that. So we are taking centroid. So now what you have to do, don't close it, go to the file, go to the export, and to the workspace. Okay, to the workspace. So here give the name to this variable. Let's say my FLC, and then press OK. So this is created in the workspace. You can see my FLC is created. You can save this in file also. During the export you have seen this option, to the file. So you can generate this file, and you can utilize this file at some other computers also, right? So just minimize it, even you can close it. So this is FLC is now made, and it is active in the workspace right now. So now let me give the inputs. So my input was 400 degrees Celsius temperature and 700 psig pressure. So for this input, let me see what will be the output action. So to evaluate this, I have the function, MATLAB function, that is eval_fis. So this is the command eval FIS, fuzzy inference system, evaluating it. This is my FLC. I mean, this is the name of this FLC variable. And here, this is how you will give your input. So your first input is related with the temperature. So the first quantity will be temperature, and second quantity will be the pressure. So you can give any value here. So since we have taken the 400 and 700 in our theoretical part, so let me see what output I will achieve. So here when I press enter, I will get the output. So output is 12.0298 degree. The same I have already shown you in my slides here as the output. This one, 12.0298. So this is how your fuzzy logic controller is designed in the Matlab. Once it is saved, okay, you can run with this command for any input. So you will get the corresponding output. You can take any other input combinations also. Let's say temperature is 500 and pressure is 600. So your output is 11.2879 degree in the clockwise, I mean positive side. So this is the overall process of designing a fuzzy logic controller in Matlab. I hope you have enjoyed this session and you have learned something new. So thank you very much for providing me your precious time. I request you to like this video, subscribe my videos and share this video to the maximum. So thank you very much once again. Have a nice time.